So I was checking this textbook by Shilov, The Theory of Linear Spaces, which is translated from the Russian by Richard Silverman. Prentice Hall, hardcover. Let me show you quickly the table of contents. So chapter number 1 here, determinants, systems of linear equations, determinants of order n, properties, expansions, cofactors down there, minors, Cramer's rule, linear dependence between the columns of a determinant. Chapter number 2, linear spaces down there, systems of linear equations, linear functions of the vector argument. And then 5 is about coordinate transformations. Bilinear and quadratic forms down there. Euclidean spaces. Chapter number 8, orthogonalization and the measurement of volume. 9 here, invariant subspaces, and 11 quadric surfaces, and 12 finally infinite dimensional Euclidean spaces. So chapter 12 is a bridge between linear algebra and analysis. So I was checking chapter number 1 on determinants, and I came across one problem. So the question is how to compute the Vandermonde determinant. Okay, so Vandermonde determinant is an application from Rn and coordinates. The first row contains ones, so 1, 1, 1 all along the first row. The second row contains the variables themselves, x1, xn, x1, x2, xn. The third row contains the variables raised to the second power, so x1 square, x2 square, xn square, and so on. So the last row contains the n minus 1 power of all the variables, actually x1 n minus 1, x2 n minus 1, all the way up to xn power n minus 1. So the question is how to compute that determinant. And indeed, the textbook provides the answer down here. So the next question is how to compute a determinant. So suppose the matrix A is given by components A11, A1n, N1, ANn. Let's consider the set of indices 1, 2, 3, all the way up to n. Okay, so this is the set of indices. And then by I1, In, all right, we will mean any permutation of 1n, okay? So I1, In is a permutation of this set of indices. So the determinant of A is the sum over all these permutations, I1, In, of the sign of the permutation I1, In, times, so we're gonna consider here n factors. So AI1, 1 times AI2, 2 times AIN, n. So we're gonna take the element I1, 1, which is the element located along the I first row and the first column. So AI2, 2 is the entry of the matrix A, which is located along the I second row, so I2 row, but the second column, and so on. So let me explain to you what is the sign of the permutation I1, In. Let's take, for example, the set of indices 1, 2, and 3. Okay, so it's the set of indices S. So let's say we start out by taking a permutation of 1, 2, and 3, say 2, 3, and 1. That's a permutation of this set down here. So what are we going to do? Well, we're going to take two consecutive indices, say, for example, 2 and 3, or 3 and 1, and then we're going to swap them out, okay? So we're going to flip 3 and 1. That operation is called a transposition. So we're going to apply here a transposition. So let's denote a transposition by tau. So we're going to apply tau to 1 and 3 because I want to pull the one at the front down there. So the first transposition will leave 2 fixed, but it'll swap 3 and 1. So 3 becomes 1, 1 becomes 3. And then I'm going to do the same thing down here. All right, on the first and the second position. So I'm going to apply yet another transposition on the first and the second positions, and then I'm going to get 1, 2, and 3. And there you have it. All right, so we started out by taking this permutation of 1, 2, 3, and then we applied 2 transpositions, one here, one there, to finally arrive at the right ordering. Okay. So this number of transpositions is what we are going to denote by, what do you call this symbol? Well, whatever, the symbol tau. Okay, so in this case, the number of transpositions is equal to 2. Okay, for this particular example. Now you could, for example, choose, the permutation 3, 1, and 2. So what would that take for us to bring 3, 1, and 2 into 1, 2, 3? Well, we might swap 3 and 1. So we apply 1 transposition here, 1, 3, and then 2. We leave the third position fixed down there, and then we apply a second transposition on 3 and 2. So we get 1, 2, and 3. So again, the number of transpositions is equal to 2 down there. And 3, 2, and 1 into 1, 2, 3. Well, we might apply a transposition down here, 2 and 1. So 3 fixed, 1, 2. Yet another transposition to swap 3 and 1 out. So we get 1, 3, and 2. And yet one more to swap 3 and 2. So we're going to get here 1, 2, and 3. So now in this case, our delta, no, what do you call that? The delta tau is equal to 3. Okay. So the sign of a certain permutation, so the sign of, say, 3, 2, 1, will be defined to be -1 power the number of transpositions. Okay. So this is going to be equal, the sign of 3, 2, 1 will be equal to -1 power 3. This is -1. Now, the number of transpositions is not an invariant of this particular permutation. What's an invariant is this number right here. Because you can bring 3, 2, 1 into 1, 2, 3 only via an odd number of transpositions. Okay? So it could be 3 or 5 or 7. And likewise, you can bring 3, 1, 2 into 1, 2, 3 via 2 transpositions, or maybe another even number of transpositions not necessarily equal to 2. So actually, the number of transpositions is not invariant for every permutation. What's an invariant is this number. Okay? So this number you see here is -1. So the sign of this permutation you see here is equal to -1 power the number of transpositions, right, that it'll take for us to bring this permutation into 1, 2, 3, n. So the determinant of a matrix A of dimension n is the sum over all the possible permutations of this set of indices of the sign of that permutation times these elements down here. Now I found a very nice example. So what do we got here? So every element is arranged as per their column. So first column here, 1, second column number 2, first column 1, second column 2. Okay, so we have a first permutation of 1, 2, which is, the 0 permutation, 1, 2, and then the next permutation 2, 1. So what would that take for 2, 1 to become 1, 2? Only one transposition, right? So negative 1 power 1 is negative 1. We have the sign down there. In the case of 3 dimensions, again, this is the determinant of the matrix we see here. We have on the left-hand side of the equality. Again, the columns follow an increasing order. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. What about the permutation 3, 2, 1? We computed that one, right? The sign of 3, 2, 1 is negative 1. And thus, we get here a negative sign. All right. The sign of 2, 1, 3 is also negative 1. And the sign of 1, 3, 2 is also negative 1. Whereas the sign of 3, 1, 2 is positive 1. 3, 1, 2, the sign is negative 1 power 2. Right? So let's now check Vandermonde's determinant down there. So we are on the first column down here. The third row contains the element x1 for the column, power 3 minus 1, so 2. All right. So likewise, the jth row, k column, contains the element xk raised to the power j minus 1. The Vandermonde's determinant is thus the addition over all these permutations of the signs of those permutations times, so this is the entry of the matrix along the first column in the I1 row. Thus, the element, so this is the, don't forget, this is the element AI11, right? So the element AI11 is x1 power I1 minus 1. And likewise, the element AIKK is thus, I forget, I made a mistake here, IK, not J, but K down there. IK minus 1. And the last element down there, the last factor is xn, IN minus 1. So if we view delta, okay, as a function of only xn, so the last coordinate, so we're gonna denote now the Vandermonde determinant. We're gonna suppose that the coordinates x1, xn minus 1 are fixed, right? So we're gonna view the determinant as being a function only of the last variable xn. Then what we have here actually is a polynomial in xn. And this polynomial has exactly degree n minus 1. Remember that the indices ik belong in the set of indices 1, 1n down there. Okay? So the highest index is actually n. All right, so this is a polynomial in xn of degree n minus 1. So we have two things, actually 3 things here. We have, first, we have that the Vandermonde determinant, when the first n minus 1 coordinates are fixed and we view it as a function of xn, this is a polynomial in xn. Second observation, delta x1, xn minus 1. So let's suppose xi is not equal to xn. Okay, so we're going to take one variable here, one coordinate, which is not equal to the last coordinate. So the question is, what is delta of xy? Right. So we come back to the definition. We see that when we replace xn by any of the other coordinates, right, x1 to xn minus 1, you find exactly one repeated column. So for example, if you replace xn by x1, then this column will be equal to the first column. If you replace xn by x2, then the last column will be equal to the second column, and so on. And you know that in that case, right, the determinant is equal to 0. Because square matrix with either a repeated column or a repeated row has determinant equal to 0. So the Vandermonde determinant evaluated at xi, when xi is not equal to xn, right, must be 0. That's the second observation. Thus, delta vanishes actually at x1, xn minus 1. All right. And the third observation is that the degree of delta is n minus 1. So now we have a polynomial in xn which vanishes at all these points, x1, xn minus 1. So we have n minus 1 such points actually, and also the degree of this polynomial is n minus 1. Thus, by a well-known result, right, from algebra, delta must be of the form. So what is the form of delta? A certain coefficient here times xn minus x1, xn minus x2 times xn minus 1. Because this polynomial vanishes at all these points, x1, x2, xn minus 1, and also it's of degree n minus 1. So we have exactly n minus 1 terms right here. Now the question is, what is A? So to determine A, we're going to expand the Vandermonde's determinant. So let's expand Vandermonde's determinant with respect to the last column down here. I'm going to put my finger down here. I'm going to delete this column in the first row and the first column. What do I get there? I get x1, x2, all the way up to xn minus 1. Then x1, n minus 1, xn minus 1 power n minus 1 down here. So I get a subdeterminant down there. Then I'm going to continue with xn down here. I'm going to continue with xn. Then I put my finger down there. I delete second row, last column. What do I get? 1, 1, 1 for the first row. Then I'm going to skip the second row, so I'm going to get x1 square, xn square, all the way down to x1n minus 1. Sorry, this is xn minus 1 down there. And then last element here will be xn minus 1 power n minus 1 actually, right? And then finally, when you reach the last element of the last column, right, you're going to get xn power n minus 1. So you get 1, 1, 1. You get x1 here. You get xn minus 1. Then x1 n minus 2. xn minus 1 n minus 2 down there. So what do we got here actually? This term right here is the Vandermonde determinant. All right, the Vandermonde determinant of x1, xn minus 1. So our delta, we can use a superscript here for the dimension. So our delta was of dimension n. This Vandermonde determinant here is of dimension n minus 1. We see that the term A is actually the leading coefficient of this polynomial. This is the nth Vandermonde determinant. So A is the leading coefficient of my polynomial, and the leading coefficient means that it's the coefficient, right, of the highest power here, which is xn power n minus 1. So this polynomial, the Vandermonde determinant, can be written as axn power n minus 1 plus, you know, the remaining terms. So so these are the terms of order, actually, n minus 2. We realized immediately from this expansion that this Vandermonde determinant, all right, in the first n minus 1 coordinates, right, must be the leading coefficient, all right? So thus the Vandermonde determinant of the Vandermonde determinant must be equal to the Vandermonde determinant in the first n minus 1 coordinates times xn minus x1, xn minus x2, all the way up to xn minus 1. So this is delta n minus 1 times the multiplication, let's say from k equal 1 to n minus 1 of the terms xn minus xk there. For the same reason, right? Delta n minus 1, which is the Vandermonde determinant of degree n minus 2 in the n minus 1 coordinates x1, x2, xn minus 1, must be equal to the Vandermonde determinant of the first n minus 2 coordinates times the multiplication, right, of, let's say, L1 to n minus 2, xn minus 1 minus xl. For the same reason. If you keep reasoning this way, you're going to find that the Vandermonde determinant in 2 coordinates, right, x1 and x2, must be equal to the Vandermonde determinant in 1 coordinate, x1, times x2 minus x1. Now, obviously, this thing is the this is just the absolute value of 1, which is 1. So this number here is 1. So this is just x2 minus x1, all right? And then delta 2, x2 minus x1, delta n minus 1, delta n minus 2, multiplication from 1 to n minus 2, xn minus 1, xl. So now, coming back to the expansion of our determinant, we see clearly that the Vandermonde determinant in n variables must be equal to the multiplication, since the first coefficient is equal to 1, the multiplication over all the indices between 1 and n, I less than l, of xl minus xi here. And so this is the expansion we're trying to get, actually. There you have it. Hope you enjoyed the video. Thanks so much for watching. See you in the next one.